Hello everyone and welcome to this lecture. Till now, we have used the matrices or linear algebra to find the properties of graphs, the structural properties or algebraic properties of graph. In this lecture, we will do the other way. We will try to find one of the very basic fundamental concept in linear algebra and matrix theory that we call determinant. We will try to find the determinant using graphs. Okay, so first of all, let us see how we actually compute the determinant. We have already computed since our 11th and 12th class, okay, but I will actually give you another way which was given by Leibniz, which uses the permutations of numbers from 1 to n if the size of the matrix is n cross n. Okay, so let us start by revisiting the formula given by Leibniz. So suppose we have a matrix of order n cross n. Okay, the formula is given by this. So determinant of A is nothing but this, summation over all the permutations. Okay, so suppose sigma tells one of the permutations, which is, and Sn is the all subset. So Sn is the set of all the permutations, permutations of numbers from 1 to up to n. We also call it symmetry group. Okay, so set of all permutations. Okay, then what we do with this permutation, it is summation over all permutation, then this. Okay, first of all, from this matrix, suppose this is general element at aij. Okay, this is n cross n. Okay, what we choose every one entry from each row. So suppose this 1, then 2, and so on an. Of course, this is 1, 2 here are depicting these rows. Then columns are selected by this, the element in your permutation. So this is sigma 1, this is sigma 2, then sigma n. So product of these n entries. Okay, so basically it's what we do, we take all possible combination of n entries such that no two entry share a row and a column. Okay, and we add them, but there is one more thing still left. Okay, what is that? That makes determinant altogether different quantity. That thing is the sign of there is a sign associated with each such combination, and we call it, suppose, sign of the sigma. What we mean by sign of sigma? Sign of basically permutation. What we mean by this? Okay, so let me actually I will actually tell what is, but before that let me actually write in a sorted form. So summation of all permutations, then sign of sigma, that we will see what this is, then product of all i's, sigma I from I equal to 1 to n. Okay, so this was the definition. Of course, we have used the Laplace expansion, and this all are equivalent. So this is same as Laplace expansion if you open it. Okay, very good. Okay, so what we mean by sign of a permutation? Okay, so let us take one permutation. Let us take, suppose numbers are n equal to 5 here, and suppose the permutation of number from 1 to 5 is, suppose, 5, 2, 3, 1, 4. I hope I have included everything. Okay, now permutation, so sign of this is nothing but, okay, sign of permutation is nothing but minus 1 to the power the number of inversions. So let me write this by this quantity. What do we mean by now number of inversions? Okay, number of inversions of what is this? So number of inversions. Okay, so let me write number of inversions. What do we mean by inversions? Okay, inversions. Okay, number of inversions. Okay, in order to tell what we mean by number of inversions, let us see what we mean by inversion pair. Okay, so suppose inversion pair. So let me define this inversion pair. Okay, inversion pair with respect to sigma. Okay, with respect to sigma. Okay, a pair of elements I and j is called inversion pair. Is called an inversion pair. If I is greater than maybe, I mean, it can be other way. So it can be other way. So I is less than j. Okay, by the way, both of these are greater or equal to 1 and lesser or equal to n. Okay, I and j both are in between 1 to n. Okay, but the sigma I of sigma I is greater than sigma j. Basically, they are out of order with respect to your permutations. Okay, now I hope the definition is clear. Now let us see this with the help of an example when the matrix is of 3 cross 3. Okay, so suppose A is this matrix. Okay, so A is your this matrix A11, A12, A13, A21, A22, A23, A31, A32, A33. What will be its determinant using Leibniz formula? So determinant of A is what? First of all, let me list down all the permutations of 1, 2, 3. So these are nothing but this, right? So yeah, by the way, let me actually give you an example of the basically what will be the number of inversion in this. Okay, can you tell me what will be the number of inversion here? Okay, so number of inversion, let me write here for this, is nothing but you see how many elements of a given element. Basically, if you pick any element, suppose 5, you just check how many elements towards the right are lesser than it. Okay, so for 5, if you see that, so basically this 2, 3, in fact all right. So this is also an inversion pair 5, 2. Okay, because if you see that I is if you see the natural order is this, right? Natural order is this. Okay, but the sigma order is this. Okay, so I is always, so 1 is less than 5, but in the ordering with respect to sigma, 5 is coming first. So this is an inversion pair. So similarly, yeah, so 5 2, 5 3, yeah, in fact everyone with respect to 5 and 5 4. Okay, very good. Okay, what about 2? Okay, yeah, 2 is just 1, so 2 1. Okay, for 3, how many? So this is 3 1. That's all. For 1, everything is good. Okay, everything is good. And for 4, there is a. So I hope I have done it correctly. Okay, so there are 6 inversion pairs. So number of inversions, so this is 6 here. Okay, so very good. So 4 for this and 1 for 2. Actually, I am again verifying this. Yeah, and 1 for 3, and yeah, so very good. So there is nothing is for 1, nothing is for 4. Very good. Now let us see for let us calculate now determinant of A. Okay, where A is 3 cross 3 matrix. Very good. So if you see, let me write down all the permutations of 1, 2, 3. So this is 1, 2, 3. Okay, then maybe actually write down. Let me in some smaller font. I will tell you why. This. So 1, 2, 3. What are others? So 1, 3, 2, then 2, 1, 3, 2, 3, 1. There will be 2 more. Okay, so 3, 1, 2, and 3, 2, 1. Okay. So now what will be the entries just by this this formula? So let us write down these collection of entries and then you are multiplying them. So this is nothing but A11. Okay, so this is A11, A1, and then this A. So basically now you assume that these 1, 2, 3 these are selected columns, okay, and rows are this A1, A2, A3, right? A3. So this is A1, A2, A3, A1, A2, A3, A1, A2, A3, A1, A2, A3. Okay, so A1, A2, A3. Okay, very good. So now you will see that there are six combinations. Okay, now along with, so each combination is with respect to some permutation, right? The permutations are this 1, 2, 3. Okay, now what will be the sign corresponding to each permutation? For this, what will be the sign? This is in their natural order, right? 1, 2, 3. So there are no inversion. The sign will be +1. Basically, inversion is 0. So -1 to the power 0 is 1. Okay, so what about this? 1, 3, 2. Okay, so I think there is just one inversion here, 3 and 2. They are making inversion, so there is just, so sign will be here minus 1. Then let me actually write this plus, this is minus. Okay, what about this 2, 1 and 3? Okay, so 3 is in right position, no, so only I think again there is one inversion pair. Okay, so yeah, very good. So this is again, hopefully I am doing it correct, sign is 1. Okay, so again 1. What about this 2, 3, 1? So for 2, 2, 1 is an inversion pair, and by the way 3, 1 is also an inversion pair. Okay, so sign here will be 2 because there are 2 inversion pair, so there will be plus 1. So let us do plus. What about this 3, 1, 2? Okay, so 1 and 2 are in the correct ordering. Okay, so for 3 there are actually 2, right? So 3, 1, 2, yeah. So again the sign will be here plus 1 because there are 2 inversion pairs. So again plus 1, and here it will be minus because it will come out to be 3 inversion pairs. Very good, just verify it, and this is the determinant, and this is the determinant. Okay, now I told you in the beginning, how can we find this determinant using graph theory or graph structure? Okay, so let us go ahead with that. Okay, the first very intuitive to think for a matrix is there always, basically every square matrix you can represent by a graph, in fact directed graph. So for example this, okay, so let us take the same matrix, okay, let me write down the diagram corresponding to this matrix. So there will be actually 3 vertices. Okay, 1, 2, 3, because there are 3, because the matrix is 3 cross 3, so we will put 3 vertices, and the number of edges between these vertices is determined by the entries in the matrix. Okay, so for example this entry will be, this edge will be actually A12. Okay, this A12, and now you see that this is a weighted, right? The weight to, so whatever the weight of A12, whatever the value of A12, that much weight we will put from edge from 1 to 2. Similarly here 2 to, so A to 1. Now let me write actually all this, A to 3, then A 2. So this direction will be what? A 3, 1, then this will be A 1, 3, and then of course there will be self loops like A 2, 2, A 3, 3, okay, and A 1, 1. Now once this diagram here, let me denote it by DA. Okay, corresponding to A. This is a diagram. Okay, now once this diagram is formed, okay, there is something called cycle covers. Okay, so let us tell what we mean by a cycle cover. Okay, a cycle cover of DA, directed graph, is actually a disjoint collection of cycles, in fact directed cycle here, directed cycles, which such that it covers, so such that all the vertices are covered, all the vertices are covered. Okay, let us take some example of vertex covers. Okay, so by default one vertex cover is this, right? You take 3 cycles. By the way, these are also cycles, right? These are also cycles. So basically, let me actually, this is 3, vertex 3, this is vertex 2, vertex 1. Okay, so let me weight them. Okay, let us take one more vertex cover. Okay, one more vertex, and maybe you take cycle from first, and then there is another cycle, maybe this is 2, this is 3. Okay, this and this is A 2 3, A 3 2. Okay, A 1 1. Okay, now in this way there will be how many other cycle covers? Okay, there will be 4 more, in fact 6. By the way, these cycles are nothing but they are corresponding to your permutations that we have seen in the Leibniz formula. Okay, what will be the permutations corresponding to this cycle? This is nothing but this 1 2 3, basically 1. So identity permutation 1 2 3, right? So 1 goes to 1, 2 goes to 2, 3 goes to 3, right? But here what is the permutation? Permutation is this. If you see that So let me write the identity permutation here. Okay, so this is your permutation corresponding. Let me write the permutation. So 1 goes to 1, 2 goes to 3, and 3 goes to 2. Okay, so you will see that with each permutation there is a cycle cover. There is a cycle cover. Okay, so there is 1-to-1 correspondence, right? The number of permutations will be same as the basic number of non-zero permutations. Now what do you mean by non-zero permutation is this. Basically, if the product term is 0, then it is 0, the 0 permutation we can call. If it is non-zero to non-zero, so whatever the non-zero permutation, that many cycle covers will be there, and there is basically these are in 1-to-1 correspondence. Okay, so basically just by knowing the permutation, you know what will be the cycle cover, and by knowing the cycle cover, you know what will be the permutation. Okay, so similarly you can write down the other one. Okay, now let me write down the formula of determinant using these structure, these cycle covers. So suppose let this, by this notation I will denote the all cycle cover, basically set of all the cycle cover, set of all the cycle covers of DA. Okay, and DA, and L will be some particular cycle cover anyway. So let me write down the formula. So the formula of matrix A, suppose this is n cross n matrix, is this: summation over all the cycle covers. Okay, all the cycle covers. Okay, then minus 1 to the power n minus n is the size of matrix. Okay, the size of matrix, or maybe the number of vertices in graph. Okay, number of cycles in L times the weight of L. Weight of L is nothing but this. So weight of L is this. Weight of L is the product of weights of the edges of L. Okay, all the edges of L. Very good. Okay, so now actually, I mean, it's very simple that you can actually verify this just by drawing the determinant by this, right? You sum over all possible cycle covers, and then you take the basically the weight of this. Weight is nothing but is just this product of these entries, right? We have seen in the Leibniz formula, this one. Okay, this part. Okay, now we have to prove that why these two things are equal. Basically, why this is same as this quantity, why this is same as summation over all, basically this minus 1 to the power the inversions of sigma times product I equal to 1 to n ai sigma I. Okay, now one thing we have already established, that this product and this are the same, right? We have this 1-to-1 correspondence between these permutations and the cycles in cycle cover. Okay, but what about the sign? Why? Now we have to establish that, we have to prove that, what? That's minus times sigma for any sigma. Okay, for any permutation. Okay, this is nothing but minus 1 to the power n minus cycles in L, where L is the corresponding to sigma, Okay, we have to actually prove this, and then these two formulas are same, right? Then these two formulas are same. So let us try to prove it. Okay, how to prove? Okay, so yeah, so let us prove it using induction, but we have to be very careful on which quantity we have to take induction, right? So prove. Okay, so suppose n minus CL is equal to P. Okay, this is some number. By the way, P will be always greater or equal to 0, right? CL can be at most how many? There can be n number of CL, right? We have seen this, right? So suppose this permutation is there. In that case, how many cycles can be possible? So basically loops on everyone, right? So loops on, there can be n cycles. So in that case, n minus n is 0. So P is always greater or equal to 0. Okay, so let us make use of induction on induction on P. Okay, when P equal to 0, if you see P equal to 0, right, in that case, how many? We have already seen that there are n cycles. There are n cycles, right? And by the way, what will be your inversions? What will be the inversion? And the corresponding sigma is what? Sigma is nothing but, sigma is this. Okay, how many inversions are there? There are 0 inversions, so 0 inversions. So basically, let me actually write now. So this is, so number of inversions in sigma are 0. So P is equal to 0. So that means what? This is proven. So write minus 1 to the power P is same as minus 1 to the power sigma for here. Like when P equal to 0. Right. Now let us assume that now it is hypothesis phase. Hypothesis. Okay. Assume that for some P greater than or equal to 0, the statement is true. The statement is true. Okay. Now if you see, now what about P plus 1? Now consider P plus 1. By the way, because P is greater or equal to 0, P plus 1 will be always greater than 0. Okay, that means the number of cycles is strictly lesser than, so that means number of cycles, okay, maybe here I would say here, okay, in that case number of cycles in CL is strictly lesser than this, right? That means there is a cycle on, there is a cycle on at least 2 vertices, okay, and moreover there are just 2 elements, I and j, I comma j, such that I is less than j, but sigma I is greater than j. That means this is an inversion pair. So maybe let me write inversion. Let us understand this help by example. Inversion pair. Okay. So suppose if you let us take one permutation which is maybe not identity permutation, then the life will be. So suppose this is 4, 2, 3, 1. Okay. So suppose this is a permutation for of numbers from 1 to 3, 4. Okay, so this is your identity permutation. Okay, so basically it says that, so what will be the cyclic, if you're saying a cyclic cover, so let us try to write down the cyclic cover here. So yeah, so 1 goes to 4. Okay, 1 goes to 4 here. Okay, and then 4 is going to 1. If you see the 1 goes to 4, 4 is going to 1. Okay, and then 2 are as it is, right? 2 goes to 2. Okay, and 2 goes to, if you see the number of cycles are less than n here, so this is yeah, same. So this is 2, this is 3 here. Now do what? Okay, similarly, yeah, do what? You swap this I and j, okay, if such is the case, swap I and j, right? So let us swap this I and j. So that means what will be the, then it will become identity permutation, right? Then it will become 1, 2, 3, 4. Okay, swap I and j. Okay. By the way, what do you think? Let's suppose this was your sigma, this is your tau. How many number of cycles in tau are there? Okay, this is not very difficult to see. Right now, if you see that the number of cycles here are now 4. Earlier it was 2, right? So 4. So in fact, whatever the permutation is, right? If you basically swap those ij entries which are corresponding to inversion pair, okay, the basically this the number of cycle increased by 1. So basically the cycle in tau are 1 plus cycles in C. Okay, so maybe this L. Okay, so this is a very cute DIY for you. This is very simple. Maybe you can take another permutation and play with this, and soon you will realize why there is just 1 increase, right? Okay, and what about the number of inversions? Okay, so what about the the number of inversions in sigma and number of inversions in tau. Okay, again this is a DIY. I will write it here. The number of inversions, the difference of basically the difference in sigma I and is always odd, is always odd. Okay, another DIY. Why this is true? You play with different permutations, okay, and you try to swap those invertible pair. Okay, you will see that the number of inversions actually change by an odd number. Okay, this actually I have given you hint how to calculate the actually inversion pair. Inversion pair of some number is nothing but you see towards the right how many elements are lesser than this. Now you are swapping. Okay, now what will be the difference of those numbers? Okay, it will always come out to be odd numbers. Okay, very good. Okay, always odd. Now next is what? Now if you see about this, right? See this, we already know that this is 1 plus C of L. Okay, okay. By the way, how the P was defined? P was this, right? P was N minus this CL. What will be the P? P for CL, basically C sigma, because sigma has tau has more number of cycles, so P for is lesser than P for basically maybe just you write this or maybe cycle of this. Okay, now what? Okay, we have already assumed due to hypothesis that for P greater or equal to 0 for that number, okay, this is always true, right? We have to prove it for P plus 1, but P for corresponding sigma is lesser than P plus 1, right? So for this, basically the statement is true. That means what? This N minus C times sigma and the number of basically this inversions in sigma has actually basically this. These two guys have the same parity. These two guys have the same parity. Now what about C? What about L? Okay, L and basically if you take about the L has just one less cycle than this, right? So here if you talk about this 1 minus N minus CL, okay, so number of cycles here, and so this is basically a difference by odd number here, but this is also a difference by just odd number, right? So these two guys will also have the same parity. So let me write down this. Okay, so again, yeah, so this is also true. Basically these two guys have the same parity, hence the statement is true or the theorem is true. Statement is true. So basically signs are also taken care when we are giving that formula. Okay, we are giving formula in terms of cycle covers. Okay, very good. I hope you understood it. If not, you can actually revise it. Very simple. You should play with different various permutations, and I mean not very hard to see. Okay, now we will talk about the determinant of the adjacency matrix of simple graphs. Remember, we have thoroughly used the adjacency matrix in this course. Okay, now let us try to find the determinant of adjacency matrix of a simple graphs. Can we make it simpler? Can we make it simpler than what we did for any matrix, because the graph was coming out to be directed? But suppose the graph is undirected. Okay, how can we find its determinant? How can we find its determinant? Okay, so suppose G is some simple graph, undirected simple graph. Okay, very good. Okay, and suppose AG is adjacency matrix, right? So how can we write determinant of AG? Okay, let me first write. Okay, let me first write the formula, and then I will tell you this immediately follows from what we have said just now. Okay, summation over all subgraphs. Now here subgraphs L are this. Okay, so it's a collection of the disjoint collection of collection of edges and cycles which covers all the vertices. all the vertices. It's again like saying, but now we have edges and cycles. Cycle here means basically, now remember in the directed case there were between edge, if you take I and j, there can be a cycle of 2 length, but now here I am taking just edge, right? Okay, very good. So everything is here basically undirected, right? As of edges, undirected edges, and cycles, undirected cycles. Okay, and suppose set of this is denoted by LA, the set of all L, set of all such subgraph or cycle cover L. Okay, so L belongs to this. Okay, now what? Nothing but n minus the number of edges in L minus the number of cycles in L. Okay, times this is now where 2 raised to power CL. Okay, CL. Why this is true? Why this is true? Okay, why this is true? I think if you see the formula again of this, in the case of generalized formula, this is very, very apparent. Okay, so suppose if you take the adjacency matrix, there will be what? This 1, 1, right? So edge and this will be corresponding. Now remember when the generalized matrix was what? So there was Aij, and we were writing the different entry for Aji, right? Because this entry may not be same, right? But in case of undirected graph, the adjacency matrix Aij equal to Ji, in fact Aij equal to Aji equal to 1, right? In that way, basically this edge is same as this one. Okay, so we are making use of this. First thing is this. Okay, another thing is what? Okay, each cycle here, so suppose if you take any cycle in the graph, right, this cycle will give, actually there will be 2 cycles corresponding to it, right? So one will be this. So okay, so let me actually first write this. Okay, so there will be 2 cycles. So one will be clockwise cycle if you talk about if you use this formula, and another will be anti-clockwise, right? Another will be anti-clockwise, and there will be anti-clockwise. So each undirected cycle is giving 2 directed cycle for the formula. Okay, now you pick any sigma or any vertex cover, right? So every cycle here is actually coming out to 2 times. So that's why we have actually wrote this 2 times, because this will be for every cycle, this will be 2, right? So 2 times the power of the number of undirected cycles. Okay, and what about this? What about this? Remember in the formula for directed case, this was nothing but n minus cycles in this, right? But here cycles are replaced by 2 things, right? So this was also counted there, but now we are counting this as an edge, right? So edge, and these are the other cycles, right? So these are the other remaining is the same. Okay, so I hope you enjoyed this. Okay, so we can write the determinant of adjacency matrix using the subgraphs in terms of basically the disjoint collection of edges and cycles. Okay, so with this I am stopping this lecture. Thank you very much. I have also learned many things while teaching. Thank you very much. Yeah.